Hello, welcome to our class on what we call the software development workflow. This is probably more commonly known as software engineering, and this is actually what I have my degree in. This is what I went to college for, is actually software engineering. We'll kind of see how it's different than regular programming, and we'll kind of first talk about the goal of software engineering, and we'll apply it in a small example, a small Hangman game example. So first we'll talk about kind of what's the point of it. What are we trying to aim, for with software engineering, and why does this exist at all? So often when we're giving a development task, we just start programming without considering the requirements or thinking about any kind of design or doing any kind of quality assurance after the program has been written. Now, the problem with this is that often our code becomes really hard to work with. It becomes what we sometimes call spaghetti code. And that's just, a pile of code. It doesn't really do anything, and it's really hard to mess with. It's really hard to work with. And a lot of the time we miss requirements when we do that. So throughout the class, we've given you a bunch of homework assignments to do, and we've kind of let you do it for the most part your own way. We've given you some guidelines with functional programming and writing comments and this and that and the other. But like I said, most of you're pretty much free to develop the software how you feel. And I'm sure a lot of you have realized that it's hard to get started writing some program, or it's hard to know that your program works after you've written it and you're not really confident in it. So like I said, software engineering looks to kind of address some of those things and a couple of other things, like how to look at requirements and kind of figure that you have everything implemented the way it needs to be. And once again, also when we do not consider the requirements or the goals of the software, we often miss requirements, and that's the worst thing. A lot of times you'll, talk to a customer and will have missed the mark, and it's very frustrating for the customer. It's very frustrating for you because they haven't, or at least you feel like they haven't described what they want very well. And I'm sure you've seen that in some of the homework assignments where it feels like you probably needed a little more details. Well, this hopefully will help you get through that and kind of how to reckon what the customer wants out of the software, or what the teacher wants out of the homework assignment. So the very first thing to think about when you're developing any kind of software is the goal of the software. And this leads us into what's called goal-based engineering. So for example, when you're developing a game, player enjoyment should always be the number one goal. And often you see this a lot, I'm sure. Developers stray away from the goal. And a lot of times it's perhaps due to they're ambitious, they want to try out a new technology or this or that or the other. But the game itself suffers and it becomes a pretty mediocre game. Or let's say you're trying to develop some software to be used by end users. And by end user, I mean any kind of user of software. So they are likely to be non-technical. Usability is very important. And this is actually one of the reasons why Apple computers are very popular, while Linux computers you hardly see. It's actually, if you go to shop for a Linux computer, they're actually hard to find. There are only a handful of manufacturers that even ship their computers with Linux pre-installed. That's because Linux, while it's very powerful, it's very hard to use. So it has very low usability. And a lot of times you'll hear these ability words, usability or portability or, testability. If the software is easy to test, those are words we often use to describe software. So we say, oh, it's not very portable, or it has low portability, meaning it doesn't work well on some system or another. And that's something that video games suffer from a lot, actually, is low portability. But to go back to this example, the goal should be very important. We should keep that in mind. So let's say you're developing a mobile app or a mobile game. Portability is pretty important because you want to be able to take that app and put it on many devices. So, there are at least iOS and Android. Usually when you develop an app, you want to build it in such a way that it's easy to port it over to Android or port it over to iOS or BlackBerry or whatever is around nowadays. So portability is very important for something like that. Like I said, for an operating system, usability. So the goal of the system, and if you look at Apple computers, you can tell that they stick very well to the goal of usability. Usually it's very easy to use. For example, my grandmother uses an iPhone, and she's never had any problems with it. She can pretty much figure it out unless it's something kind of technical. So usability is very good. And once again, that goes back to the goal. So they've kept this goal of usability in mind, and they've achieved it. So in this example, there may be two ways of implementing some feature. It's always better to go with the implementation that better suits the goal. And hopefully, as you make more programs and write more code throughout your careers, you'll keep this in mind that, like, a lot of times the professor will be looking that you know how to use a certain concept. Here's another goal. So a lot of the time in the homework, I hope that you know how to use something. I don't want you to go and Google how to do something different. I want you to show me that you can do the concept that we just learned in class. So once again, kind of think back and reckon for yourself what the goal is. Why am I writing this software? Yeah, so if we come here, so why am I developing this? Or what is the customer or the teacher or whatever, what are they looking for in the software? What's the goal of the software? And you should always look back, like I said, at pretty much every step and consider the goal. And that's what you call goal-based engineering. So once we've finally come up with a goal, we know what we want the software to do generally. It's time to kind of break that down a little bit and talk about what are called requirements. And requirements are just the specification of features that need to be implemented into the software. So you need the software to do things. And the requirements specify how it should do that, what those things that it needs to do are, who should be doing those things, so on and so forth, why the software needs those things. The requirements specify those. And there are many, many ways of specifying requirements, but the most common way nowadays are what are called user stories, along with some wireframe mockups for UI components. UI, of course, means user interface. So anything that the user sees, you might have some wireframe mockups. And we'll discuss user stories and wireframe mockups next. So user stories are just a natural way for non-technical people to explain some feature of some piece of software. Like I said, they're the most common form of requirement specification nowadays. So user story just follows this template as some kind of user type. So as a user or as a player, if you're talking about a video game, or as an accountant or as an account holder, as a user type, I want to blank. So I want to goal so that, and then you have some reason. So for example, I think I have some examples. Yeah. So for example, as a player, I want to save my game. So player is the user type, game is the goal, so that I do not need to restart my progress every time I turn off the console. And once again, this may be a user story for some video game. So let's kind of step over each of these three things. So the first piece that you have to plug into this formula here, so user type, the first piece tells us just kind of what type of user is using the software. And this is often useful for grouping features together. So you might have a feature set for admins of the software. You might have a feature set for regular users. So being able to specify the kind of user that's using this particular feature in your software is really helpful a lot of the times. So as a blank, or as a player, I want to save my game. So this is the kind of, you can call it the meat and potatoes of the requirement, or of the user story. So this tells you what the software should be able to do. So save my game, this tells you that your software needs to be able to save the game. And like I said, this is the bulk of the requirement. This is, you could think of it as the most important thing in this requirement, because it tells the programmer what they need to write. And then so that, once again, I do not need to restart my progress every time I turn off the console. So this part is possibly the second most important part, this so that clause. And that's so that we can actually tie it back to the goal. So the goal, let's say, of a video game is to be enjoyable and not frustrating. If you have to restart your progress every time you turn the console off, that's not enjoyable and it's pretty frustrating. So like I said, this so that clause is actually very important. A lot of people skip this clause, but that's a pretty bad idea when you need to think back at the goal of the software or of the game or of whatever you're developing. So like I said, let's work on the next example. So as an investor, so maybe it has to do with some investing software. So as an investor, I want to be able to check my account balances so that I can make business decisions quickly without having to check each account individually with external systems. So once again, as an investor, that's the user type, I want to check my account balances. So this tells the programmer or the developer that they need to be able to check account balances. This is the core feature so that I can make business decisions quickly without having to check each account individually with external systems. So maybe the goal of this software system is to be able to trade and work efficiently within the software itself. So maybe you've been contracted to write some software system that, some investing software that the key feature is that it integrates everything together. So the goal is integration or or you can say interoperability, where it interoperates between all the different systems. So that could be a goal. And this so that clause points to that goal so that you're sure that this feature matches with the goal so that you're writing the right software. And sometimes these features might not make sense. And this is sometimes what's called feature creep or scope creep, where your customer comes at you with 1,000 features and only 50 of them are even applicable. So this so that clause helps non-technical people and technical people look back at the goal to make sure that the software that they're writing is actually worthwhile, or that the feature that they're thinking of is actually worthwhile. So let's look at another example. As a passenger, so this is going to be for some flight booking software here. As a passenger, I want to be able to check my flight status so that I can arrive at the airport at the right time. So once again, as a user type passenger, I want to be able to check my flight status. So this tells the programmer that they need to program this ability to check flight statuses so that I can arrive at the airport at the right time. So once again, the goal is for the software system, the goal is to organize flights. And this goal, having passengers arriving at the airport at the right time, is pretty important when you're organizing flights. So this is just another example. So once again, as a player, so maybe this is going to be the Hangman game that we're going to talk about. As a player, I want to input my letter guess so that I can make progress in guessing the secret word. So the goal is to guess the secret word of this game, is to be able to guess the secret word that the Hangman program picks out randomly. So as a player, I want to be able to input my letter guess one letter at a time. This tells us that we need to write this feature of inputting some letter so that I can make progress in guessing the secret word. So these were some examples and kind of an explanation of what user stories are. And once again, what these do, it's often, even if you're just writing an assignment for class, it's often useful to list out these features. So before you start writing, or perhaps if you get stuck writing your program, it's useful to just organize yourself by writing these simple statements out, these one-liners. And that kind of lets you know what you need the software to do and, why this feature is important. Maybe you have an open-ended assignment and you need to decide which of these features is important. Well, we have these so that clauses that take us back to the goal of the software we're trying to write. And we could decide, okay, maybe this feature isn't actually even that important. It doesn't relate to the goal. It's superfluous, you could say. So that's kind of an overview about user stories. So this is pretty important. Not every requirement has to be covered. 100% requirements coverage is a waste of time, quite frankly, because we can handle ambiguities by looking back at the goal. So we'll see when we write some requirements for this Hangman game, we're not going to cover every single requirement. We're not going to cover every single key press. We're not going to cover every single button click, because the programmer needs to have a little bit of flexibility to make the program work, according to the goal. So 100% requirements coverage is, unless you're developing something that's super critical, life critical, like let's say a radiation machine that dispenses chemotherapy or whatever, unless you're working on something life critical, then 100% requirements coverage is pretty much not necessary. But the goal is we want enough requirements specified to be able to develop the software that meets the goal. Further iterations of the software will get the software working according to the full specification. So usually what happens is that we get a handful of requirements and we can kind of develop the system according to those requirements. And then we go back and forth a couple of times through a couple of software iterations, maybe 2, 3, maybe more, depending on the kind of business you're trying to do. But a handful of software iterations, and that's where actually everything gets nailed down. So maybe they don't like the font. Well, that's not going to be specified in requirements. That's going to be specified in person because the person you're demoing the software to says they don't like the font. So once again, we really just need enough requirements to get going. And as we go down the road, as we iterate a couple of times through the software, that's really when you'll meet the mark. You'll hit the mark with what the software needs to do. So we talked about, if we come back to requirements, we talked about user stories. We kind of have an idea of what user stories are. And next we'll talk about wireframe mockups. So wireframes are just used. They're simple diagrams that are used to specify the layout of some user interface, or maybe a website, maybe an iPhone app, but let's see some example. So here's a web page that's been laid out. So it has a search up here. This looks like some sort of online ordering system where you can view a cart. Looks like maybe Home Depot even could, maybe looks a little bit like this, but it's just very simple. You don't need the actual images here. You just need a very simple layout. And a lot of times you'll get something like this for a web page and you'll be asked to develop according to this. So you're not going to be left completely in the dark. A lot of times customers will pretty much know what they're looking for and give you something like this and a handful of use cases, and you can figure out what you need the software to do. But for a console app like the Hangman game that we're going to write, this isn't important, something like this, because there's no user interface. Everything's through the console. So it's useful to just grab some graph paper and kind of sketch out what you want the web page to look at and kind of see it in person, and draft some requirements, draft some use cases, and that'll help you get going on what you want the software to be. Next, so we have our requirements. We've discussed the goal. Next, we'll talk about architecture. So after we know the goal and understand some of the requirements, we can start with a high-level design of the software. This is usually just a simple box and arrow diagram. Most of the time, this is just done on a whiteboard. You'll get everybody that's working on the project. You'll kind of sit together. You have a short meeting, usually a stand-up meeting, where everybody's at the whiteboard with a handful of pens, and you're marking on the whiteboard trying to figure out what the software should generally look like. Or I should say what the underlying, what the implementation of the software should generally look like. So the purpose of discussing software architecture is to have a high-level understanding of the system being developed and to explain it to other developers. Once again, of the high-level design. That's the key word here, high-level. So let's see some example. You don't need to know the actual concept here, but there's some data layer. Maybe this is a set of databases. We'll say these are 4 databases. We have a data access layer. So this code here reads the databases. This service layer just, it just basic web services, basic internal services. And we have a business layer that has all the logic, all the if statements and for loops and stuff would be here. And then a presentation layer, the actual user interface, which you might get something like this, a wireframe that actually describes what the user interface should look like. So this, you could call it as a layered architecture, because it has all these different striations, all these different layers. This is usually very common as a layered architecture. Pretty much every software I've worked on has some sort of layered architecture built into it. But once again, this is just a very high level. So you just grab a marker, grab some paper, grab a pen, and kind of sketch out, just using boxes and arrows, generally what the software should look like. Very simple. So now that we have the very high level understanding, so we know that there's going to be data involved, we know that there's going to be user interface, we'll have some logic in there, some if statements and for loops and stuff, some basic programming stuff. Now that we know that, we can actually move on to what you call the software design. So this is what, most of your time should be spent on when you're developing some piece of software, is the design. So in the design, you start working out the specifics needed to actually write the software. This involves deciding which packages to use, how the data should be represented, the database design, just to name a few examples. There are many, many things that you can talk about with software design. And once again, this is just a high-level overview of software design. There are entire degrees dealing with just software design. And this is kind of interesting, and I wish people would have told me about this a lot earlier. Since so many software systems are similar, like this software system here, I'm sure every single person who's worked in some sort of business as a software engineer or as a software developer has seen this, has seen a data layer plus a data access layer plus a service layer plus a business layer plus a presentation layer. Every single web developer has seen something like this. So since so many patterns are seen throughout software, since so many software systems are so similar, you can use what are called design patterns. So these are just a very common expressions of software systems. And we'll see a few examples in a little bit. So the second thing I want to cover here, so a lot of times you'll pick out a design pattern, and that kind of allows you to talk to other developers about what the software should do kind of in quicker terms, or kind of without having to explain every little bit. You can just say, oh, this is just a pub sub or a publisher subscriber, and pretty much people know what you're talking about. So design patterns allow people to communicate effectively, and they allow people to reuse existing ideas effectively without having to think about it all yourself and come up with everything yourself. So design documents come in many forms, but the most common are what are called UML, or Unified Modeling Language Diagrams. So first, let's see UML. And once again, this isn't going to be part of the class. I'm just trying to show you that this exists in general. So here's what you would call a UML class diagram. And each of these, each of these symbols means something. So there's actually a difference between the filled in black triangle, and there's no triangles here that go into feed into these boxes. The black triangles mean something. The 0 ... stars mean something. All of these things mean something. Now, I'm not going to go into it. There's plenty of resources online about UML. I just wanted to show you guys that this is kind of what a software design might look like for a piece of software. And a lot of times once again, so the point of this whole lecture is just to, if you're stuck writing software, if you don't know where to go, or if you think you've gotten it wrong and you're stuck, these are tricks and tips on how to get out of that rut. So UML is one of those examples, or in general, software design is one of those examples. So if you get stuck, the best thing to do is think about the goal. Next, you look at the requirements and maybe draw out a wireframe. But let's say you get through all that and you still don't know what to do. Well, the next step is to do a high-level diagram of what you're trying to accomplish with the software. So maybe you have databases and business, all these things. Whatever your application is, be able to just describe it very briefly in one picture. The whole thing should be describable in one picture. That's the software architecture. And then you go into software design. Let's say you're still stuck. Maybe you've written a little bit of code, so you generally know that you're going to have format and size, location, duration. You're going to have these properties as part of this, what you would call technical class, or whatever this happens to be. Generally what the software should look like, but you need to kind of sit down and think about it a little more. That's what UML is for. Now, there are many other features, but for this class, for what I want you to take away as beginning programmers, that the software design it's there to help you think about what to do next and how you want the software to look. So one of the ways that helps is with UML. And the second way is with some design patterns. So these are probably the most common design patterns. We have abstract pattern. Every programmer pretty much uses this without even knowing it, using abstract. There's going to be singleton. Singleton's very popular. Prototype's very popular. A lot of these are, that's why they're here on some common. A lot of these are very popular. You'll see these from time to time. And once again, the point of the class isn't for you to memorize these. It's just for you to know that design patterns exist. And once again, that UML exists. And maybe you do some research if you get stuck and you learn about some of these, the abstract patterns, what you need to finish off the software that you're writing. The whole point, the whole goal of this lecture is just to help you get out of ruts when you get stuck programming. So software design is one of those things where you just sit down, maybe you sit down with a whiteboard, maybe some graph paper, and you draw out a diagram like this. It doesn't have to be like this. It doesn't have to be technical. You draw out some diagram like this that kind of explains. And we'll see an example with the Hangman game. Hopefully that'll make a little more sense. What I'm talking about with this. And we don't actually use UML. I just want to kind of introduce it. But so design patterns, some common ones, plus UML. I want you to know that those exist. So next, we actually have designed the software. In a perfect world, we would have had to designed it and we'd have perfect requirements and everything. But next, we're ready to start the implementation. So now that we've designed, we're ready to start programming. When we write our software, we want to make sure that we're meeting all of the requirements and following the design that we develop. So once we've developed the design, we think it's good. We want to follow that design. It does no good to sit down and think about a design for 6 hours if we're going to just throw it away. And once again, we're meeting the requirements given to us by the customer that we've kind of worked on ourselves with the customer. We want to make sure we're meeting those requirements. Also, we should follow the standards that we discussed in classes, like, for example, using many small functions, naming variables and functions properly, documenting the code with comments, using functional programming, so on and so forth. We need to make sure when we implement our software, we actually follow those standards. It's very important. As discussed within previous lectures, why these things are so important. Next, we should be proud of the software we develop. So we don't want to just, let's say you're turning in some assignment. You've kind of done some sort of pseudo design just to kind of come up with the way the software should work. Maybe you've come up with some requirements because you got stuck and you kind of need to know what the software should do. We're ready to implement it. We should be proud of that implementation. We should be professional with that implementation, meaning that we shouldn't write spaghetti code. Professional developers don't write spaghetti code. Professional developers write comments and small functions and name variables well, so on and so forth. Professional developers do those things. So we should be professional with our software. We should follow the standards. We should use, design patterns if they fit well. We should do those things. We should know generally how software works. And finally, we want to be pragmatic in understanding the system we're developing. So what we mean by pragmatic and professional pride and pragmatic, those are terms used by the software craftsmanship community to give them credit for kind of this definition here. Basically, if something's pragmatic or if we're pragmatic developers, this means that if something's unclear, we should look back at the goal and make sure that the decision that we make in implementing the software meets the goal of the system and it meets the requirements. Even if the implementation is more difficult, we should always think about the goal, think about the customer. So for us, the goal is to make the customer happy 90% of the time. Whether that's our boss or our teacher or whatever, whoever has asked you to write the software, we should make them happy. So really what that means is a lot of the time we have to think for ourselves. We're not robots, we're human beings, and we can reason and reckon things. And we have to use those abilities of reasoning to be better engineers. So that's what we mean by pragmatic, is really that we have to reckon what would be the best for the software, what's the best for the customer. Once again, whether that's an actual customer who's paying you or it's a teacher or whatever it may be. We have to be pragmatic. So the last thing, so that's kind of, once again, this whole class has been about software implementation. This is kind of just a very brief overview. We've talked about it enough all semester, but next we'll talk about quality assurance. So we have our goal, we have requirements. We did our architecture, a very simple overall drawing of the software system. We did the design. Maybe it's a handful of documents that we drew out just to kind of organize ourselves. Now let's talk about quality assurance. We've written the software, of course. After we've written the software, we need to make sure it works. We need to make sure it's what the customer knows or wants. And it's important to know that we're confident in the software we're delivering, whether it's an assignment or whatever. There are many kinds of testing. There are degrees on testing, on software testing, not just one. There are a handful of degrees on this even. But there are two in particular that every developer in the world should know, what are called negative testing and boundary testing. Every developer needs to do negative testing. Every developer needs to do boundary testing if it's applicable to the code they're writing. So negative testing simply involves inputting bad input values and making sure the program handles the input well without crashing. So for example, for writing a calculator, and the user inputs an invalid character or an invalid, let's say the ampersand or something, it shouldn't crash the program. And so far in this class, we've pretty much ignored that. We say, okay, you can let it crash the program just because we didn't know about error handling, which we talked about a few lessons ago. We didn't know about the try except, or in general, what's called error handling. We didn't know about those, so we kind of let it be. But from now on, when you should pretty much have proper if statements that handle improper inputs, you should have try except to make sure that your program doesn't crash, so on and so forth. So once again, for example, let's say you're writing a program that provides a letter grade given a number grade. So one quick example, let's say you input 89, that's a B. If you input 95, that's an A. If you input 50, that's an F. So we want to test these following inputs. We want to test -1. We want to test these negative inputs. Or, not negative as in -1, but we want to test these non-valid inputs. Maybe you can call it non-valid testing, but -1 is what you call a negative input, not just because it's a negative number. 101 would also be a negative input, just because 101 doesn't make sense in the business domain. A letter grade or a number grade of 101 out of 100 doesn't make any sense. A, so the letter A. This doesn't make any sense when you input A and you ask for the letter grade. It might make sense in some domains, but it doesn't make sense here for this example. And once again, this ampersand. So when the program asks you for a number to convert into a letter grade, an ampersand doesn't make any sense. So we want to try a handful of these, and we kind of want to be a little clever about it. So if we test -1, we can pretty much assume that every negative value would handle pretty much the same as -1. If we test 101, we can pretty much know that every value above 100 should handle the same. And that actually takes us to the next type of testing, which is called boundary testing. So boundary testing involves testing the functional boundaries of your input space, or testing the boundaries in general. As well as the most extreme values. So you want to test each functional break in the input space, and we'll talk about that in a second, plus some slightly smaller value, plus some slightly larger value than the boundary. This is done for numerical values. So, for example, that's once again the same program that we just discussed. Let's say you have a program that takes in some number grade and gives you a letter grade. We definitely want to test 0. So we handled the invalid inputs earlier. We handled -1 and 101. We don't need to worry about negative numbers. We already tested that. But 0 is what you would call a boundary. It's the lowest possible value within the input space. So 0 is a good value to test when you plug it in. Once again, 70, depending on how your grading works, 70 is a functional break. So anything less than 70 should be an F. And then anything between 70 and 80 should be a C. So that's why we test 70, because it's a functional break within the input space. We test 69 because it's a value slightly smaller than the break, and we test 71. So these three are kind of grouped together. 69, 70, 71 are grouped together around the 70 value because it's a logical break or a functional break within the input space. Same goes for 80. So 80 to 90 is a B. So we test 79 because it's some value slightly smaller, 80 because it's right at the break, and then 81. And same logic once again follows for the 90 range. So 89, 90, 91, because anything greater than 90 should be an A. And then of course we test 100 because it's the largest value of the input space. So as you can imagine, if you have a calculator, you can have a lot of different functional boundaries. Probably when you're doing testing multiplication, you should test a negative times a negative times a positive, a negative times 0, so on and so forth. All of those combinations you should probably test when you're writing some sort of calculator here. And of course, with the negative testing, things like if you do like P times F, that doesn't make any sense. So that shouldn't crash the program, but it should be handled properly within the program. Maybe you print an error and ask the user to retry. So that's handled by negative testing, and then what's called boundary testing. Now, boundary testing isn't always applicable. Like if you only have letters you're inputting, only negative testing makes sense because you don't have any values or any ranges you can be testing. You pretty much only have letters and characters and things. So the Hangman game, the only thing the user can input are letters. So we'll have plenty of negative testing. We'll want to test a handful of random characters, but we won't have any boundary testing because there are no numeric values that they're typing in. So just quickly go over this one last time. So the very first thing we need to do is come up with a goal. With that goal, we can write some user stories and maybe do some wireframe mockups to kind of organize ourselves to figure out what software we're trying to write. After we have that, it's often good to come up with a general overall view of the software you're trying to develop. So this is called the architecture. Kind of a 50,000 foot view of the software. And here's just one small example of that. Usually it's just boxes and, labeled boxes and arrows. Sometimes the arrows are labeled, sometimes not, doesn't matter. Software design. So this is a little bit more in depth. Now you don't need to know UML in particular, but this is one example of, software design. Software design might look something like this. And then we have some design patterns. We want to, maybe you learn a couple of these on your own. It'd be pretty, I think, valuable. It might be pretty hard for beginners, but I've always said that the number one thing that a beginner programmer can kind of do to advance themselves to be kind of an intermediate or even a lower level advanced programmer is to know some design patterns and to be able to use design patterns. But so software design is usually very focused on things like UML and expressing design patterns in software design. So for you, we'll see an example of the Hangman game, maybe what you could get away with. And then implementation we talked about. You've had the design, you have the requirements that implement based on those two things. And then quality assurance. Now, once again, you could probably make a list of 100 things here that you could test with software, but here are just two: negative testing and some boundary testing, like we've discussed. So finally, let's talk about the actual Hangman game. And let's actually apply this to take something like this prompt to turn it into some actual code. Okay, so we'll start with the problem statement. We want to make a game of Hangman, where a user guesses a letter until they either run out of guesses or they guess all the letters in the word. Guessing the same letter twice does not count against the remaining guesses. That's good. When they run out of guesses, the word is displayed in full. So either they run out of guesses, and of course if they guess all the letters, it'll display the word in full. Of course, they'll know what the word is anyways. After a letter is guessed correctly, the display needs to reflect the position of the correctly guessed letter. We'll talk about that in a second as well as the possessions of all unguessed letters. So this is actually the end of these slides, but let me clarify on this last 2 points. Let's say the word is hang, so it has 4 letters, and you've probably seen this a lot when you play Hangman. And then let's say they guess the letter A. We want to show something like this with these underscores or some sort of character. Maybe they're asterisks or something. But we basically want to tell the user that the second letter here is the letter A that they just guessed. And then let's say they type in a G, it'll be like this. And then N, and then of course they'll try H. So as we play the game, we want to replace these asterisks or maybe underscores or whatever character we kind of decide to use. We'll replace those with the actual letters that they guess. And then underneath it, you might have the incorrect letter. So K, U, T, E, F. So some letters that aren't correct, and then A would of course be correct. So, and then the final thing we would pretty much have is a guesses remaining. And let's say we have 3 guesses remaining. So this is pretty much what because we're just using the console, all we can do is output text. This is pretty much what our program would look like from here down. So we'd have this, the word with the individual letters blinked out, and then you'd have our incorrect letters, and then below that, of course, you'd have your guesses remaining. So I'm just going to add a new slide, and we'll talk about what the goal would be. So what's the goal of this program? So it's, of course, to write a program, and we'll just say Hangman game, and what's the goal? So I would argue that the goal is to make a fun Hangman game, Hangman, that works well and is not frustrating to use. So I would argue that this is the goal. So of course we have to make a Hangman game as per the prompt or the problem statement, but let's focus on a couple of other things. So it works well and it's not frustrating to use. What I mean by that is, it doesn't crash all the time, and it accepts, like, if you type in, let's say you're 6 letters, and let's say you're about to guess the word and you mistype and you accidentally type the same letter that you guessed before twice. Well, that shouldn't count against you. It would be frustrating if you lost when you're about to win just because you mistyped, or if you accidentally type in a non-valid input like an apostrophe or something. Let's say you accidentally type something like that. It shouldn't crash the program. So it's pretty frustrating when stuff like that happens. It shouldn't crash the whole program for invalid inputs. So our goal is to make a Hangman game. Maybe fun is ambiguous. Fun's probably not a good part of the goal, although it should be, of course, the goal to make it fun. But let's just say make a Hangman game. The word fun's a little bit ambiguous. What is fun? How can you define it? Fun's different for different folks. So we'll just say make a Hangman game that works well and is not frustrating to use. Now, of course, this is still pretty ambiguous, but we get the point. And we'll just grab a new slide and we'll call this we'll just call it user stories. So let's come up with a handful of user stories. Let's come up with, let's say, 3 or 4 of them. So once again, if we go back to that format, it's as a blank. So pretty much we only have one user of the software, which are players. As a player, I want to, let's come up with the first and most important thing in this game, is to actually be able to interact with the software, to be able to input. So let's say I want to input my letter guess so that I can get closer to guessing the word. So this is pretty straightforward. As a player, when we have one type of user, I want to input my letter guess. This you could think of as the most basic function of the whole game, is to input the letter guess so that I can get, so that I can get closer to guessing the word. So the goal for the player, of course, is to guess the word, so that I can get closer to guessing the word as a player. So here's one requirement. So what would you say the next most important thing is? I'd probably say that you want to keep track of the unguessed letters, because it'd be frustrating to have them have a piece of paper and pen to have to keep track of the letters that they guessed. The software should do that for them. So once again, as a player, I want to be able to see my incorrect guesses, so that, why would a player want to see their incorrect guesses? So that they can, I would argue, so that they can better plan their next guess. There are probably lots of reasons, so that they don't have to write it down, so that the game's less frustrating, but we'll just say for now, so that I can better plan my next guess. Pretty simple requirement. So what's next? So something else that would be pretty helpful is to see how many guesses or how many attempts they have left. It'd be, once again, pretty inconvenient if they have to, maybe have a tally of paper. Every time they make a guess, they'd have to tally something up. That's pretty inconvenient. So once again, to make the software less frustrating, we want to be able to show them how many guesses they have left. So as a player, I want to be able to see my remaining guesses. And there are probably lots of reasons why a player would want to see the remaining guesses. But I'll just argue that, so that I can better plan my next guess. Similar logic to the last. These are pretty similar. So these both have to do with the view. They want to be able to, Once again, these are, if you think about it, these could even be considered convenience. You could tell the player that they have 5 guesses to guess the word. And then they have to keep track of the letters that they guessed, and they have to keep a track of how many guesses they have left. So these are both, you could argue, as convenience. But once again, when we go back to the goal, we want software that works well, i.e. doesn't crash and it's not frustrating to use. So we're trying to minimize frustration based on this goal. And we can do that through these 2 requirements. We can kind of mitigate any frustration they might face. So, and of course, you could even argue as the second, in fact, I'll put it here, as the second most important goal is to be able to see the letters that they've correctly guessed and the position of those letters. So as a player, I want to be able to see a representation of the guessed and unguessed letters. So once again, as long as you tell them how many letters are in the word, and you tell them when they guess correctly how, where the position of those guessed letters are, as long as you do something like that, then technically this is a convenience, but I would even argue that this is so inconvenient to have to keep track of all of that they probably not want to use your software if you didn't provide this kind of feature. So once again, so that, and you could argue that it's convenient, so you can just say so that I can better plan my next guess. Okay. So of course, this is the most important functional thing. So we want to be able to input letters. I mean, the game's unplayable completely if you can't input letters. Next, this you could argue either way. You want to be able to see a representation, and it'll probably look something like this with the underscores and then the guessed letters slotted in, so that they can kind of plan out their next guess, and they can kind of see what their next guess would be based on something like this. And then, of course, they want to be able to see their incorrect guesses, which we can come back to as here. These are the incorrect. And let's actually mark this. These are the incorrect guesses here. And then finally, they want to see the guesses remaining, which is here, of course. So actually, and we've come up with the goal, and we've actually come up with a handful of user stories. And this is as far as we're going to go with the user stories. We can actually start. This is, of course, going to be the first requirement we're going to do. We'll start with this. We'll next write this requirement. We'll do this next, and then we'll do this. We'll kind of go in this order to make it easy to implement it. But this kind of represents the wireframe. So we don't have something graphical like, this we have, but we've kind of laid out the console in a way that we like. So this will be what we consider a wireframe. And we'll just grab this. And we'll just call this Hangman game. And we'll call this wireframe. And then we'll add a couple of things. And then we'll say, please input your next guess here. So our console would look kind of like this. And how we'll achieve this is we'll render these line by line. And then whenever something changes, we'll clear the console out and we'll redraw it. We'll reprint these lines. So we'll print the lines. We'll say input a next guess. They input the guess, and then it clears the console and then updates this based on the guess. Updates this content based on the guess. So it'll basically be draw it, wait for the input, clear it out, redraw it based on the update, based on the game update, based on a correct or incorrect guess. So either it's going to go here and decrease guesses remaining, or go here and not decrease guesses remaining. And then, of course, please input your next guess would be here. So this is what we could call our wireframe. So now that we kind of have an understand of what we're looking for, let's just go Hangman game. Let me grab this off this on their screen. Okay, so let's talk about the software architecture. Software architecture. So the architecture is going to be very, very simple. In this case, it's just a console application. So it would really look something like this. This guy represents a user. A lot of times when we're drawing on whiteboards, we just draw a smiley face. That's the guy. That's the user. They use the console to work with the game logic. So we have this kind of interaction. So the user sees the console, and the console sees the game logic, but the user kind of doesn't directly see the game logic. And this is almost a nonsense architecture, but just to show in general what a software architecture might look like for this game. Just a really simple, you have a guy that works with the console to play the game. Okay, so that's the architecture. Once again, it should just be extremely simple, a one-page type design. Not even a design, just a one-page type explanation of what the system might look like. And finally, we'll talk about the design. Okay, so now's the time to start kind of thinking about breaking it down. So the very first thing that happens in a Hangman game is that the Hangman game chooses some word. Now we could have all of the words hard-coded into the actual application or the actual Python file, but that's going to be really inconvenient. It's going to be hard to maintain, and if we want to change it, we have to redo or we have to modify the Python file, which might cause trouble. So let's actually store the words. We'll have one long list of words, some dictionary of words within a file. So we'll just say read word list from file, get a random word. So this is part of the design we've just decided. See, and this is sort of the difference between an architecture and a design. So we could include the file here, but we're kind of delving down. We're kind of deciding how we want the software to work at a lower level. So what's the next thing? We know that we have to do something over and over again. And that something is to get the word. To get the input, the user's input, and check it. And that's going to be in some sort of loop. So we know that we're going to have some sort of main loop. So we'll just say main loop that accepts user input, validates the input. This is important because we don't want the program to crash. We need to be able to validate the input and reprompt if the input is invalid. So validate the input, then check the guess. So that's pretty simple. One loop, and you can kind of already start to see how the software is going to break down. We have, this should be loop. So we're going to have a main loop. So you can imagine there's going to be some sort of while loop in here with some conditions, and we're going to have a raw input here. We're going to have some if statements here. Maybe even do a try except. Maybe we try to convert it to a letter, and if the letter conversion works, we know that the input's invalid because we don't accept we don't accept numbers. So if they input a number, so there's various ways of validating the input. But okay, then check the guess. So this is going to have some sort of this name. We can already kind of see how this is going to break down by just simple writing it down and thinking about it a little bit, and then we can actually think about what check the guess means, and that's going to be something like if the letter is correct, update the display, and of course for us that's a console, indicating the newly correct guess, or newly correct letter even. We can say letter. So we want to be able to update the display, and we mean change this part of the display, or you'll say we'll clear the whole display, but that'll come later during implementation. But we want to basically update this if the letter is correct. Next, if the guess is wrong, add it to the list of incorrect and decrease the number of tries remaining. So the only thing we've done here, the only thing we've done here is kind of break it up a little bit. So we know what the game needs. We know generally what the user experience should be. We know how it should kind of look in a console. Once again, this doesn't have to be perfect. This is just to kind of get us on our feet to where we can start programming. We know from a very high level that pretty much the user is going to interact with the console, and the console, through the console, will get an input from the console, will display to the console, back to the user. And then we know some basic features of our software based on this design. And we can actually take this, and we'll do that next. We'll just do it right now. We can take these features, and you can kind of see how this is starting to look. You can start reading some code into this. So read from a file. Well, we know how to do that in Python, get a random word. Well, we studied random last class. We know how to make a main loop. We know how to accept user input. We know about validation. We know kind of what this means by check the guess. We've kind of broken that down into a couple of steps. So we want to display it. Or if the guess is wrong, add it to the list of incorrect letters. Well, we know that there's going to be a list involved, a list of incorrect letters. In fact, the name of the variable is probably going to be list of incorrect letters. Probably something like this, because it's descriptive and it, matches our design pretty well. So once again, we'll just go design. And usually when you have design, it'll look something like this. Let me actually just do this. Let me just paste the whole slide in. It's going to be a little bit easier. So let's actually present this. Usually this is pretty easy. This is sometimes called a roadmap or a flow diagram or a flow chart. It's usually pretty helpful to have a start place and an ending place. So, we just kind of put these up here to organize ourselves. So what's the very first thing we need to do? If we look back at this design, we know for a fact we need to get this random word from a file. So the very first step, get a random word from file. It's pretty easy. We'll have this method, we'll write this method, and that's probably the very first line of code is going to be get random word from file. Next, we know that we have this main loop that accepts user input. Now, we can kind of break that down a little bit. So while remaining tries is greater than 0, and word guessed is false, or you can think of it as while the user has tries remaining and the word's not guessed, then we move into this loop. And you can kind of see the loop going around right here. But let's say that the remaining tries is 0. Or let's say that they did guess the word. What we need to do instead of going through this loop, we need to show win or lose, whatever that means. We can kind of design it a little bit more later if we need to, but that's just going to take us right to the end. So probably the flow of this software is going to be start. We're going to get the random word. We're going to hit this loop, iterate through it a few times until one of these two conditions, either they run out of tries or they guess the word. It'll pop here, show win or lose, and then I'm going to display the end. So let's expound a little bit on this main loop here. So we know that we're not going to need to get user input and validate user input, and we can even make these methods, make these simple method calls. So we know we're going to get user input in some method and validate user input in some method. So the very first thing we do in this loop is get the user input. Next, after we've gotten this user input, we need to check that the input is correct. So if user input is correct, this is going to be some function. If user input is correct, if it's correct, we'll just go and update the correct guess, and we're going to go through the loop. So we're going to update correct guess. Of course, that would be back here, updating something like this, because it's correct. And then we'll just hit this loop again. We'll keep going through this loop. But if the user input is not correct, we're going to update incorrect guess. So it'll update like this. So it'll add this to the list, and then it'll decrement this. Actually, we have that here. So you update those incorrect guess. And this would probably just be guesses, or even better. Let's be a little bit better even. List. Update incorrect guess list, which is going to be this list right here. So we'll update that by adding that guess to it, and then decrease tries or decrement tries. And then once again, we keep going through here. And then when we finally hit this, when one of these conditions are either they're going to run out of tries or they're going to guess the word, once again, show win or lose, and then end the program. So that kind of covers the Hangman example. And of course, actually, I think there's one more thing. Well, no, I didn't have it, but we can add it really quick. the last thing, of course, we implement, um, which we'll talk about kind of in the next class. We'll talk about, I'll actually go through and I'll implement this project so you guys can see, now that you kind of know what a while loop is and an if statement and how to get random numbers, and you understand those things, you can actually follow through as I develop something like this. And this is how I would actually do it. If I was given an assignment, and I did this a lot in college, of course, you first think about the goal. That might be to get a good grade. And how do you get a good grade? And you might have sub goals here. So how do you make this happen? So let's say we don't want the program to crash. So this is one sub goal. Don't want to waste users' time. That's another sub goal. It's frustrating when you have your time wasted. So you get, of course, have sub goals. So when you're doing assignments, and once again, this doesn't have to apply to computer science. You can have a regular homework assignment in history or a paper in history. You think about the goal first. What's the goal of the paper? Well, it's to get a good grade. Okay, of course, but let's break that down. Let's go and come up with a few sub goals. Okay, well, maybe you need to talk about Lincoln, and maybe you need to talk about George Bush or whatever, right? Whatever history. You can break that down into sub goals. So don't think that this is limited to this class. This is, in general, one way you can think about engineering is you kind of start with the goal, and this is definitely what you call goal-based engineering. And then you can break it down into requirements. So you can say, like for the history example, as a reader, I want to learn more about Lincoln so that, and then this is pretty important when you're talking about writing papers. This expresses this so that clause expresses the idea that you're trying to get across in the paper. So once again, you know, don't think about this, don't limit this to software engineering. You can use these user stories in general, and you can use this idea of flowcharts and diagrams in general through all kinds of career paths. But in the world of software, usually we'll have some goal, write some user stories, write some sort of basic UI just to kind of know what we're talking about, do a really basic architecture. And then kind of what I do is, it's nice to sit down and kind of make a bulleted list like this about what you want the software to do in general. And then from that bulleted list, you can start breaking it down into these basic blocks, these basic logical blocks. And the last thing we want to talk about are some of the quality assurance. So we don't have any numerical input, so we don't need to do no boundary testing. So we know that's good. That's nice. All we have to do is negative testing. So let's think about some of the test cases that we could pass into this program. So we want to make sure that lowercase letters work as well as, uppercase letters work as well as lowercase. So those are two pretty good test cases. One of these, actually both of these should be okay. Let's say some random symbol. We'll take a handful of random symbols. Let's take a really weird one, like the back tick up way in the top of the keyboard. Let's take some numbers. Let's take maybe a negative number. And these will be the test cases. So under these scenarios, none of these inputs should crash the program. The program should pretty much be able to accept all of these. And then, of course, just a blank space. And then, of course, null space. So all you do is maybe you hit the input key twice. So you didn't pass anything to the program. And I think that should pretty much cover it. So maybe you just press space and hit enter, and maybe you just hit enter twice or something. None of those should crash the program. So we don't need boundary testing, but here's some of the test cases. And it's good, once again, to kind of think about some of the test cases before you start programming. And actually, a lot of times you can start at the end of the program and kind of work your way backwards. So show, win, or lose. So, we'll pretty much do it from the front all the way to the back. So from start to end. But, as kind of a tip, it's sometimes pretty useful to start at the end. Maybe you start with these test cases and you start at the end and you work your way backwards. Sometimes that's pretty helpful on some programs. Sometimes in data structures, if you study that in your higher level classes, it's often pretty useful to start backwards. Start with the test cases. And this is actually what you would call test-driven development. So we talked about goal-driven development a little bit earlier, or goal engineering or goal-based engineering. Test-driven development, actually, it's interesting. It takes the test cases and starts with those, and you always start at the end and you work your way backwards to the beginning. But so anyways, I hope you found this at least somewhat useful. And I hope you guys can, apply this in some way, some part of your life. And next class, we'll actually talk about, I'll actually sit down and I'll program this Hangman game based on these requirements. And I'll take this design and we'll kind of build it out based on this design. And maybe we'll do another practice. We'll have another simple exercise where I, break this down for you guys, how you actually maybe do an architecture diagram that's a little more advanced. But none of this is going to be on the final. This is just mostly for yourself, FYI, to, hopefully be able to think in different ways and apply this to different parts of your life. Anyways, so thanks for listening. Good afternoon.